we have a die, right? We have a die, and for some by some means, and this so we have this is the raw material, and this raw material will be extruded from the original shape and to the final shape. So look at the first one, the direct one. So here is the die. So this is a container. So here is extrusion. So this is a pressing. This is a pressing steam. This is a die bake. So here is the die bake. Here is the die. This is a billet. And this billet is a raw material. Originally, my raw material is so big, but because there is a pressing stem, and so this guy keeps pressing this one. So this orifice, a small orifice, you can just think this is a liquid. So this liquid is coming out from this orifice. I'm saying quotation mark liquid. So this one is extrusion, right? This is a direct extrusion because of this is the very huge the pressure from the bottom. So this guy can flow from this orifice and to come from so big and to this so small. So this is called the direct. It's a direct extrusion. And second one, indirect. Second one, this is extrusion. Is a billet. Is a back. Is a disc container. Here is a die, and this is a dummy block. This is a two-step. So here you just compress it. Okay? Just compress this one and falling out. No, I'm sorry. So now this one, this is a two-step. So this is a two-step that goes in the opposite way. In the opposite way, you compress it. You compress this guy. So there's an orifice. So this is a billet. Billet means raw material. This raw material have nothing, have no place to go except this orifice. Then just like the water liquid coming out from this orifice. That's the reason this guy is called indirect. And third one, so this is hydrostatic. The hydrostatic, we have the seals here. So this is a pressing stem. This is a fluid. As you can see, this is a fluid is inside. Whenever you see fluid hydrostatic, what comes into your mind? For me, I would say the pressure from all directions is the same. Is that right? Hydrostatic pressure. So here is the hydrostatic. This is a fluid. I compress the fluid. Okay. So this is raw material. It's placed in the this is the fluid. So I press it, then this guy will come out. Right? So this is a direct. This is impact. And suppose this is my tool. This is my final shape. I say suppose at the very beginning. So there is at the very beginning this is a bulk material, and then I press. This is a punch. Right? This is a punch. And go all the way down. So here it will be the tool, extruded tool. And this might be the final product. So you can just the bulk, so big a bulk, and because the punching, and I have a final, this is extruded tool. So there are four different types of extrusion. So direct one, indirect as a relative, another relative motion between this is between the die and this is extruded material. The third one is hydrostatic, and fourth one is impact. So this is a slide and shows gives you details. This is exactly what I just told you. So you can just keep a look. Okay. Direct extrusion, indirect extrusion, in hydrostatic extrusion, and impact extrusion. Maybe in some homework. The next homework, I will ask you on what are the commonly seen types of extrusion we have. Like, just tell me this. That's good enough. Right? Then the parameters that used for describing the extrusion processes. There are three. There are three parameters. And so this parameter, this one, I like this one because I'm a mechanical engineer. And I like this the ratio. This is a ratio. The third one, I told you about the third one. This one is a original cross-section area and divided by your final cross-section area. Original cross-section area is the cross-section area before you extrude the material. The AF is a cross-section area, final cross-section area after it coming out from the orifice. So this is the ratio. So this is the extrusion ratio. The other two, first one is circumscribing the circle diameter, called CCD. The diameter of the smallest circle into which the extruded the cross section will fit. So this is called CCD. And second one is the shape factor. And shape factor is a ratio of the perimeter of the part to its cross-section area. Perimeter is the perimeter and over is a cross-section area. We have these three different the values to describe the extrusion the processes. So this is CCD and shape factor along with extrusion ratio. So personally, I like this one because it is very intuitive. So here are the examples of extruded product. It's very beautiful, right? For this one, so this is long stock. You can, based on your needs, you can just cut it into multiple pieces. So here, how can I get this one? Suppose I have the raw material. I just have a die. On the die, I have this kind of orifice. Then by some means, I can just compress, just push the raw material into this orifice. Look at this one. Right? If you have played, why was it played? I play with the mark, right? Mark, right? The mark and the mark. I can just build a lot of shapes based on the mark. So here is another one. So here is also this is a stock, and based on your needs, you can cut this one into multiple pieces. How to get this one? How to get this one? The same thing. You have a die, lay on the die, and you have this desired shape of the orifice. And then you compress the raw material, and then finally you get this one. Definitely, this is extrusion will consume a lot of energy, and it requires very highly sophisticated this is equipment. The same thing for this one. So here are some examples. This is a very beautiful one. This is our section, as I said, and this one can be a very huge block. The final one, based on your needs, you cut it into multiple pieces. So we know the metal flow. This is the flow. Flow one. Whenever we hear the flow and the water, we think about this as a fluid. The water is moving. There's a flow. So here is the die. Okay, this is so here is a material and here is orifice. The same thing for all these three pictures. We have this is orifice here, and by some means, so this is the raw material is being pushed, and this raw material will go through this one because of the pushing force. So here are several the observations I want to talk. So first one, for the figure A. So the most homogeneous flow pattern is obtained. So it's talked about here. When there is no friction as the interface, and you can see, right? And for our homework 2, you can just change the frictional coefficient between the plate and the top of the raw material. And you can play a lot of different parameters. Frictional coefficient between the plate and this the top of the material, and you can play with the different temperature and to see how the temperature and the frictional coefficient affect the performance. So this is a lot of fun. Actually, you do not need to use much more extra time. You just after you finish the original one, just change some parameters and start it again, and you can compare. Right? You will have a very first-hand information about this comparison between these two models. And that's very good. As I said, it is optional. It is not required. But if you do it, I will be very happy. If you do it and let me know, I will give you bonus. How does that sound? Right? I will give you bonus if you do this extra work. I will give you bonus. This bonus will be kept until the final grade. If for the final grade, for some reason, and you just, for example, you get 92.89 something, and I can fill you in. Okay?
Send us a Canvas reminder. Also, a little announcement, just to make sure you're
You mean the owner?
Yeah.
I make announcement, right? If I make announcement, the announcement will be kept in the camera all the time, right? Sometimes? Yeah. I encourage you to do it, but it's, as I said, it's not mandatory. I know you have a lot of other work. Right? So here, there's a friction. You can see that if we assume the friction equals 0. But actually, the friction is not equal to 0. If we want friction to be as less as possible, you can just apply some lubrication. That is additional work. So, second one, when the friction along all the interface is high, see, you can see very, very clearly this is homogeneity, inhomogeneity here. So homogeneity disappears. See, this one and this one is totally different. And we have they called dead metal zone develops. This is called dead zone. So the high shear, because the shear with friction, if the friction coefficient is high, the high shear area as the material flow into the die exit, right? Similar to liquid flow into a funnel. I'm sorry. This configuration may indicate that the billet surface and could enter this high shear zone and be extruded and cause defects in the extruded product. So here there might be, because of friction, we might have these defects. So this one, right? So this is the third configuration. So this is the highest shear zone extends further back into the billet. See? Back into the billet. This one is just a little bit here, billet. But here, it's go all the way from here to here. All this is friction because of high friction. This situation can be due to high container wall friction, which retards the flow of the billet, or from the material in which the flow stress drops rapidly with increasing temperature, such as the titanium. Titanium is very, very tough material. In hot extrusion, if we elevate the temperature, the material near the container walls cools rapidly, because this outside, this is ambient, this is atmosphere. Whereby the material becomes stronger as a result, the material in central region of the billet flows towards the die more easily than that as outer regions. So why this happens? Two reasons. First, there's a high friction between the wall and this is the material. Second, and near the wall, in an area that is near the wall, and the cooling rate is high, the temperature is low. And in the center, the temperature will be higher. That in the center, the material moves much easier than the material moves near the wall. So that's the two reasons that we can have this kind of extreme case. So this is you can see far away from here to here. So this is just one dead zone that is not very, very big, but here is the dead zone is bigger. So if I ask you, and why, when we compare these two, can you tell me why and what condition we have this one? Two reasons, right? First reason that high frictional coefficient between the material and the wall. Second, and because near the wall, the temperature is low, temperature is lower than the temperature in the middle. As a result, the material in the center will move faster than the material near the wall. So that is these two reasons that we have this longer dead zone. So this is intuitive. This, I think, if you have difficulty in understanding this one, and we can talk further. Good. And so here are some calculations about the metal flow. So ideally, so if we do not have friction, and so this pressure that is needed can be calculated using this equation. So this is y is write down as if you have some this tablet or whatever other smart devices, or maybe just write on your notebook. So what is YF? Yield strength. Y here is yield strength. Sometimes they use SY, sometimes they just use Y. So I want you to know Y is the yield strength. So this A0 is the original cross-sectional area, AF is the final cross-sectional area. So if we have friction, and this P can be described using this equation, this is mu here, this is the mu. And this is tangent alpha. You can get this is extrusion pressure with 45 dead zone, dead metal zone. So this is P. You can use this one. If the dead metal zone we have 45, this one can be simplified a little bit. So this alpha is the dead zone. This is angle as the extrusion pressure. So this is the R. Okay? R is a ratio of this A0 to AF. R is a ratio. And how to get this equation? And just steal from the force balance equation from the scratch using the force balance equation to get this one. If you are interested, and you can use the abacus to do it also. Right? Abacus. Actually, I need to tell you this is kind of empirical equation. It's not very, very accurate. And there are a lot of assumptions here. Understand? For the accurate results, I would suggest you use abacus to do it. To do the simulation and do the convergence test, and then do validation, and then to get this result. This is the proper way to do it. But this is, as I said, this is empirical. Where empirical equations are not accurate, very accurate, the reason is that when they describe these empirical results, and they just have several assumptions. These assumptions are not correct. I'm sorry, I should not say that. These assumptions sometimes are far away from the reality. That's the difference between analytical results and empirical results. Empirical results, we have some assumptions. So sometimes these assumptions are totally wrong. So actual force. So here is use this one to get the actual force. In actual extrusion practice, as well as in other metal working process, and we have difficulty in estimating the coefficient of friction and its variations throughout all workpiece side continuum surface. It is very, very difficult to identify the frictional coefficient, right? You agree? Very difficult. Second one is the flow stress of the material under the actual condition of temperature and the strain rate. So this one is, you need to do a lot of experiments to identify the exact flow stress is a theory, the flow stress equation. And third one is the work involved in the inhomogeneous deformation. A simple empirical formula using this one. Okay, so A and B and are experimentally determined constants. It has been determined that approximate value for A is this one, B is this one, and B from 1.2 to 1.5. As I said, this is empirical. Right? Before I talk about this slide, I told you there are a lot of assumptions that these assumptions are not correct. So here are the three reasons why, and when they estimated this one, and they are not very, very accurate. This is the results. This is very, very hard. Right? Sometimes for the mechanical engineers, and sometimes we need some assumptions, and then we compare our results with the experimental results to see and for how different our results are from the experimental results. Then we know how valid the assumptions are. So here is the optimum. So because the force, okay, because the force, and we can do this is the optimum, the diangle. The diangle, you know, diangle is because this is my original cross-section area, and then out this orifice, there's an orifice, right? Orifice. So if I press this is the billet, press this raw material, So this material can flow from some surface or from some orifice. This angle, and this is called a die angle. The die angle has has an important effect on process in extrusion. Why? Because if the die angle is very huge and it needs more phase, more forces. So the effects can be summarized as follows. Right? So this is die angle. I'm showing you what the die angle is. So here is the die angle. If we have a die here, this is die angle. It's hard to see. This is the angle. This angle. Wherever this angle. So this angle should not be the rectangular shape. If this one is rectangular shape, that's a singularity. That is very bad. It should be a slope. It should be the cone, like the cone. So from here. From this one and to this one should be a cone. So the ideal force, so this is the effect of the angle. The ideal force is function of the speed that the material undergoes. Yeah, definitely. That's a function of this extrusion ratio R. R equals A0 over this AF. Consequently, it is independent of the die angle. If there is no friction. Okay, if there is no friction, that's another story. If the force due to friction increases with decreasing die angle, the force due to friction increases, and with decreasing die angle. If the die angle decreases, the force will be bigger. Why? Because from the figure 6.47, the length of the contact along the billet die interface increases as the die angle decreases, and thus the work required increases, as shown by the curve D, this one. So the C, so additional force is required for redundant work and due to the inhomogeneous deformation of the material during extrusion. This work is assumed to increase with the die angle, and because the higher the angle, the more non-uniform the deformation becomes. So here are three effects of this is the die angle. And if there is a need, you need to come back to get this result. Well, you don't need to memorize. You do not need to memorize, as I said. All these are facts. You just know where you can get these results. If you have very, very good memory, memorize it. And we'll have a talent show. You can just showcase your lesson. Okay, so the parameter that is used to estimate the force in hot, the extrusion is experimentally determined extrusion constant. And remember, this is for the hot extrusion. And there is an extrusion constant, Ke. And this includes various factors involved in process. So this P equals Ke log R. Remember, this is just a little bit of variation from our original equation, right? So be very careful. And some value of Ke for variety of materials are given in this figure. So you can see the Ke for the same material, the Ke is decreasing as the temperature increases. This is understandable, right? If the temperature is high, less energy will be required. Less energy will be needed for the extrusion. Do you agree? The higher temperature, the softer the material will be. And so as a result, less energy will be required for finishing the extrusion. So be very careful. And how can we calculate this Ke? Right? This Ke and usually determined experimentally. So here, so extrusion speed, definitely extrusion speed, and this extrusion pressure, extrusion speed also very, very important. The reason is that the higher the speed, the more energy you need, right? Do you agree? Usually when we extrude something, if there is we want material to flow slowly, but in order to improve the productivity, or any other reason we want to extrude very, very quickly. If this is the case, and definitely you need more energy. So this is logarithmic the diagram. So as the extrusion speed increases, and this is the pressure increases, needed pressure increases, that is more energy is needed. If the increase the temperature, it decreases. You can see. So this is for different temperature. This is the lowest temperature. I'm sorry, this is the highest temperature, this is the lowest temperature. So this is extrusion constant, and P equals this one, right? As I said, for different materials, even for the same material, as the temperature increases, and this is the Ke decreases. The reason is that the higher the temperature is, the softer the material will be. As a result, less energy will be needed. So then we talk about cold extrusion. Cold extrusion means that we do not elevate the temperature at all. So look at here. The first one. So here, this is a two die. This is a die. Is a punch. If you compress it, and you will have this is the direction of the material flow. So this one is no temperature change. For this one, we have a die here. Is a punch. This punch. If we compress this one, yes, and so this is the material flow in this direction, and definitely comes from this direction. This will have a tube. This will become a tube. This is a final product. So remember, this is the cold extrusion and needs more energy. So here are several advantages of cold extrusion, just like the advantage of cold forging over the hot forging, because of temperature. Temperature sometimes plays an important role. So this will improve the material mechanical properties, resulting from steel hardening, provided that the heat generated by plastic deformation and the friction does not recrystallize the extruded metal. If there is a plastic deformation, usually plastic deformation accompanies with the heat. What do you know why? Because the plastic deformation usually consumes energy. Okay, so this is the heat. This is energy is not conserved. I'm sorry, the energy is always conserved, but some energy dissipates in the form of heat. So if the heat is high, the heat might cause this material to recrystallize. That is another story. If this is the case, it's bad. Right? The second one is a good control of dimension tolerance, because the temperature is not very high. The dimensional accuracy will be much better than the counterparts you get in the hot extrusion. So that's requiring a minimum of machining and finishing operation. If for the hot extrusion, if the dimension is not very accurate, you need to do the post processing. And usually, how to do the post processing? Machining, the different machining, turning, this is drilling, milling. Also, this is other advanced manufacturing processes, laser machining, and EDM. EDM is electrical discharge machining, and also this additive manufacturing. So there's many ways to do the post processing. So all these advanced manufacturing technologies will be covered after we finish all these required things. Okay, that is the recent topic. This is a topic in the manufacturing processes. And the last one is improve the surface, and still because of low temperature, and partly due to the absence of outside fumes, and provide that lubrication is effective. So temperature, if the temperature high, and we have bad dimensional accuracy, we have bad this is a dimensional tolerance, and also the bad surface, and also we might have oxides on the surface. The last one is high production rates and relatively low cost, and because you don't need to have a hot oven and to elevate the temperature. So usually high production rates, and we have also the cost is low. So this is not always, very not always, but sometimes, most of the time. So here is a talk about impact extrusion, impact. So this is schematic illustration of impact extrusion process. So this one are stripped using the stripper plate. So this is a blank is raw material, and this is a die. This is a stripper plate, and come down. And as always, they may stick to the punch. So here is using a strip plate. This is a strip plate. Two examples. The collapsible tubes can be produced by impact extrusion, referred to as a Hooker process. This is the tube, collapsible tube. This one. So here is the punch. This is acceleration zoom in. So here is the die. So this is the material. You can see the yellow one is the material. If this is a punch, the heat, this is the material, because there is a clearance, and the material will flow this way. Right? So here's and finally you will have a tube. So it generates products that the tubular shapes with wall thickness that are small in relation to their diameter. So the Coke, I think the Coke is a Coca-Cola, the containers, the beverage containers are extruded. So concentricity of the punch and the blank is important, as otherwise the wall thickness will not be uniform. Yeah, definitely the concentricity of this punch and also concentricity of this die is very, very important. Right? You can imagine if this guy is a little bit off in this direction, what will happen? So that means this wall will be thicker, will be thin, and this wall will be thicker. So that is a uniform wall thickness. That's bad. So then we talk about hydrostatic extrusion. Hydrostatic, as the name suggests, and there is a fluid, and the fluid is surrounding the raw material. So the pressure here required for extrusion is supplied through the fluid medium that surrounds the billet. Billet is the raw material we are working on. Pressure in this type of process are typically on the order of 1400 megapascal. This is very, very high. It's about 1.4 gigapascal. It's high, right? So here is the extrusion ratio with respect to maximum extrusion pressure. And definitely, as the extrusion ratio increases, so this pressure needed will be increasing. Is that right? Yes. So because extrusion ratio is a bigger, that means extrusion ratio equals A0 over AF. If this one is R is bigger, that means your final cross-section area will be smaller. As a result, more energy will be needed. So here, for this one, as a function for the direct extrusion, all of 90 degrees. So this is the angle. So hydrostatic extrusion, all of 45 degrees. So this is 25 degrees, half of this one, B and C. You can see the angle, if the angle is lower, and it can fly more. This is the pressure is needed is smaller. The D is idealized homogeneous deformation. This idealized angle that this is for the comparison only, right? This is for the comparison only. So because always when we extrude something and there is a friction, we will not have a homogeneous, we will have inhomogeneous deformation instead. Then we talk about defects. The commonly seen defects in the extrusion. There are three. First one is the surface cracking. So surface cracking, the cracks on surface. So if the extrusion temperature, speed, and friction are too high, the surface temperature can rise significantly, and this can lead to the surface cracking and tearing. Right, so this is the surface cracking. Second one is extrusion defect. So this kind of the type of metal flow shown in this figure will tend to draw the surface oxides and impurity and toward the center of the billet. And this effect, known as extrusion defect type of kill pipe and fish killing, render a considerable portion of extruded material useless by as much as 1/3 of the length of the extrusion. Why? Because the oxides and other impurities are induced and in the billet. So this sometimes especially if you are using the final products, it's very, very expensive, and so it can be a problem. So this you should know this one, okay? So this effect, and this effect actually is some surface oxides and other impurities, and the surface oxides and other impurities are introduced and in the billet. As a result, the material is not as pure as you think. So this might be the defect. It depends on how you are going to use this final product. So this defect can be reduced by, and there are several ways to minimize and or reduce this one extrusion defect. First, modifying the flow pattern to a less inhomogeneous one, and such by controlling the friction and minimizing temperature gradient. So if the friction is low, so this one will be you can just reduce this defect. And can somebody tell me what is a gradient? Whenever you hear a gradient, and what comes into your mind? Gradient.
Like a slow change. So a gradient?
Yeah, gradient.
Yeah, like a slow change, actually, or like a slow.
Some maximum
Yeah, kind of a gradient, whatever gradient. Okay, so here in our case, the temperature gradient. Gradient means something is varying in terms of the position. Do you agree? So this temperature gradient means what? Temperature means gradient means that these are two neighboring points and how different the temperature is. So this is called gradient. The high temperature gradient means that this temperature, the temperature at this point, and the now temperature at the neighboring point is high. So this is called high gradient, right? Now, whenever you see the gradient, it means that something is varying in terms of the positions, locations. So this is, you should know, the temperature gradient. Temperature gradient, high temperature gradient means that this is the temperature is uniform substantially. And low temperature gradient means that the temperature are very, very comparable, right? So this gradient. So this is the first one. Second one, machining the billet surface prior to extrude to eliminate the scale and the impurities. Let's see another way and to remove these impurities before extrusion. And third one, using a dummy block that is smaller in diameter than the container, thus leaving a thin shell along the container wall as extrusion progresses. This is the third one, use a dummy block. So this is the second defect. And third one is internal cracking. Internal cracking is very, very difficult to control. So cracks, which we call the center burst or central cracking. So arrowhead fracture or is a chevron cracking can develop at the center of the extruded product. And these cracks are attributed to a state of hydrostat tensile stress as the center line. Okay, so tensile stress is bad. If we have tensile stress, and that might result in the crack. Questions? So here are three different commonly see the defects in extrusion. Any questions? So here is a chevron cracking defect. So this is this internal cracking. Okay, this internal cracking. So we look at here. This is a die. This is a raw material, rigid billet. So it goes this way. You can see here central burst. So if this is the case, we have defects in our furniture. So the tube. So here is on how to extrude the tube. So here, this is a container. So here the yellow one is a material. For some reason, this material it can be flowing. So we have this RAM. This RAM can be compressed by some means. And in addition to this RAM, we also have a mantle. This mantle can have relative motion with this RAM. And you can see, what I want is a tube instead of a solid cylindrical, right? So how can I do that? I have a mantle here, so I only allow, my system only allows the material to flow along my mantle. So as a result, I will have a tube. Without this mantle, what you get will be a solid cylinder. So this is the first one, use internal mantle. So B is using a spider die. A spider die with a just like spider. So here is a spider die. This is a spider die. You can see here is the block. Here is a part of the die. Here is a part of the die. Here's a part of the die. On this one, I have 4 orifices. 1, 2, 3, 4. If I put this guy here, okay. If I put this guy here, because of this spider, 1, 2, 3, 4, it's a spider-like things. And this is material can only flow through these 4 orifices. As a result, we can get this kind of the tubing. So another one is extrusion of hollow shapes. These are hollow shapes. As long as you have this kind of die, and you can just have these hollow shapes. This hollow actually is you have the material in this on the die. So as a result, this material can only flow. This will not flow through this part on your die. So as a result, this is hollow. It will be hollow. Okay? So this is the first one for aluminum intention ladders is a ladder. Okay. Second one, B.D components of various types of die for extruding intricate and hollow shape. This is intricate. This is a die, different die. This die has orifices. All right. So this is orifice 1. This is orifices. This is inlet ports. And this is a porthole die. Right? So this is a spider die. So this is a bridge die. So these are pretty much for the extrusion. And any questions so far?
Unlike the spider guys, so it's like once the material goes through and like remelt and welds together afterwards, it passes through like the bridges gaps.
The spider die?
Yeah.
Spider die, this is here.
Yeah. So once it like those little bridges, does it like the material reconnects afterwards and welds?
Yeah, the material goes for this gap. This is orifice, this orifice, this orifice, and this orifice.
And then it reconnects afterwards, and then
Yes. Any other questions? No question? Okay, well.
So this is kind of like the same question. So with the spider die, it doesn't break it up into 4 pieces. It would come back into 1 because it goes through each of the 4 like quadrants. Wouldn't that break up the work piece into 4 pieces?
So this will come out. This is material come out from these 4 orifices, right? So here, this. This is a spider die. So this is a spider die. This is a main job. This is a main job. Okay, I need to take a look at this one. Okay, so I will talk about this one Monday.